For centuries, we've been searching for a new Earth, trillions of dollars in telescopes, thousands of scientists, a single goal, a new beginning for humanity. But we were wrong, terribly wrong, when the James Webb Space Telescope looked at the planet K2-18b 120 light-years away. It found everything we were searching for, a paradise covered in water. Yet, in the atmosphere, there was a gas that shouldn't have been there. Dimethylsulfide. On Earth, this gas is produced almost entirely by one thing: life. This planet is 8 times larger than Earth. And the signal is so clear that the margin of error is next to impossible. But that isn't the real shock. The real shock is that the new home we were looking for already has an owner, if you are ready to face the fact that we are not alone in the universe. Like the video and subscribe. Because the answer to humanity's greatest question is about to change forever. We begin. For years, we believed Earth was the only planet that harbored life in the universe. This unique magma blue sphere was our only refuge. Because wherever we looked, we saw an emptiness, an infinite darkness and silence. But that assumption is no longer valid. NASA has identified more than 4,000 potential planets. Not just similar to Earth, but far better than it. So, everything we thought we knew is about to change. This list even includes 24 special planets, with conditions more comfortable than our own. Now we know. The universe might be far more hospitable than we ever imagined. Yes, so we must confront this concept of super-Earths. So what makes a planet a super-Earth? It's not just a definition based on size. It also means having conditions more favorable for life than our own. A more stable climate, a richer potential for biodiversity, a much longer lifespan. And this is where KO-I5715.01 enters the picture. Let's just call it KOI. Because this planet is one of the clearest examples of what an ideal world could look like. It's located in the Cygnus constellation, a full 3,000 light-years away from us. That distance is roughly 29 quadrillion kilometers. In other words, reaching it with today's technology is impossible. But what's truly interesting isn't its distance, but its features. KOI is nearly twice the size of Earth, so its gravitational pull is stronger, and stronger gravity means it can hold on to a thicker atmosphere. This thick atmosphere protects the planet better from harmful cosmic rays. It also retains heat for much longer. The average temperature on KOI is 11 degrees Celsius, a little cooler than our planet. But thanks to its powerful atmosphere, the perceived temperature is likely much higher and more comfortable. This planet seems designed, like an incubator, for life to emerge and flourish. So, what makes such a perfect world possible? It all starts with having the right star. The planet KOI orbits an orange dwarf. Our star, the Sun, is a yellow dwarf. Yellow dwarfs aren't bad at supporting life. But orange dwarfs do the job much better. Because they are the marathon runners of the universe. Our Sun has about 7 to 8 billion years of life left. That's a little more than Earth's own age. But orange dwarfs can live for 45 to 70 billion years. This immense lifespan provides 2 major advantages. First, we could live on a planet for a much longer time. Second, and more importantly, life would have billions more years to evolve into complex forms. So, scientists believe that a planet orbiting a roughly 7 billion-year-old orange dwarf is the best place to find advanced organisms. The koi we are studying is 5.5 billion years old, so it's not at the ideal age. But on our Earth, which is 1 billion years younger, life somehow succeeded. So, koi may not have shown its full potential just yet. It's quite close to its star. It completes a year in just 190 days. This means it receives plenty of the energy that life needs. But it's not enough for a planet to just orbit the right star. Being in the habitable zone is no guarantee either. There is another critical factor. This factor is related to the planet's own posture. Its axial tilt. The habitable zone is the ideal temperature range where liquid water can exist on a planet's surface. Mars is also in the Sun's habitable zone. But today it is a bone dry, frozen desert. Because Mars's axial tilt is extremely unstable, this instability caused the oceans that were once thought to exist to evaporate completely. This is where Kepler 186f comes into play. It's 490 light-years away from us, about 5 quadrillion kilometers. They call it Earth's cousin. Because its size and axial tilt are very similar to our own. This similarity means the planet likely has stable seasons and a regular day-night cycle, just like on Earth. This stability provides a vital foundation for life to take hold. But Kepler 186f is not perfect either. It orbits a red dwarf. Red dwarfs live even longer than orange dwarfs. Yet, they are much dimmer and colder. So, even though Kepler 186f is closer to its star than we are to ours, its sky is likely in a perpetual sunset red. Also, being the same size as Earth is a disadvantage. Because an ideal planet needs stronger gravity, for a thicker atmosphere and more protection. As you can see, what makes a planet habitable depends on a delicate balance: the right star, the right orbit, the right size, and the right posture. All these factors must come together. But a recent discovery by scientists has added a new and shocking variable to this equation. Among all these theoretical super-Earths, the James Webb Telescope focused on one, and what it found was not just a possibility, but concrete evidence. So, how can we know with such certainty what's in the atmosphere of a planet hundreds of light-years away? And why does that tiny molecule, hiding in that atmosphere, change our entire search so fundamentally? Because what Webb saw was not just a chemical trace. It was the whisper of life. And this whisper showed us that a planet doesn't have to be an exact copy of Earth to host life. Because the universe's recipes for life might be far more diverse than we know. So, scientists are now studying not just Earth-like planets, but also water worlds with great excitement. This is where Kepler 62e and 62f take the stage. These two planets were once called the celestial bodies most similar to Earth. But they are not copies of our planet. They represent a whole other possibility. They are located in the Lyra constellation, a full 1,200 light-years away from us. This pair orbits a red dwarf. Kepler 62e is particularly noteworthy because it's about 1.5 times larger than Earth, and it completes one orbit around its star in just 122 days. This fast orbit means the planet receives plenty of energy. But the most striking thing is the prediction scientists have made about these planets. They believe both could be almost entirely covered in water. Imagine the entire planet consisting of a single, gigantic ocean. If there is any land, it's likely just archipelagos, inert like our Hawaii. For some, this is a dream, an endless ocean and tropical islands. But for others, it's a nightmare. Because, on such a world, you would never know what lurks in the depths of that ocean. Stories of ancient sea monsters, like the megalodon, might come to mind. Yet, colossal creatures that have evolved in an ocean for billions of years could be far beyond our imagination. So why are these water worlds so important for life? Because they completely demolish the idea that life is dependent on land, and perhaps the most common form of life in the universe isn't developing on land, but in the depths of oceans. This possibility is shifting our search in a completely new direction. But it's not all about water. For a planet to be crowned a super Earth, it needs to have other critical features. These features don't just make a planet habitable, they make it ideal. This is where we meet the planet named K-3010.01. This planet is perhaps the most concrete example of the ideal world formula. Its average temperature is 19 degrees Celsius. This is slightly warmer than our planet. But this is exactly what scientists are looking for. Because, according to them, the ideal planet's temperature should be about 10 degrees higher than Earth's. A warmer planet means more comfortable living conditions and a higher potential for biodiversity. SO-KOI-301.0.01 passes the temperature test with flying colors. What about its size? Its radius is about 1.5 times that of Earth. This gives it stronger gravity and a thicker atmosphere. It's thought that 60% of the planet's surface is covered by oceans. This is less than the 71% on Earth. More land means more resources and living space. But this is not the most shocking piece of data. When all these factors come together, scientists calculate the probability of finding life on KOI 3010.01 to be 84%. This is one of the highest rates ever quoted in the search for life in the universe. This is not speculation. This is a mathematical probability, based on available data. Of course, this doesn't have to be intelligent life. But the chance of at least animal-like organisms existing is very high. So, what would these creatures look like? Creatures evolving on a planet with stronger gravity would probably be very different from what we know. To resist gravity, they would need a stockier and more muscular build. Perhaps they would have large bodies, but short and powerful legs, a sight both cute and terrifying. But all these planets, all this data, are just tiny dots in our telescopes. We only have boring numbers about them. We don't even know exactly what they look like. The theories are fantastic. The possibilities are exciting. But we now want to move beyond assumptions. We are no longer content with just saying, maybe. We want to see real proof. Also, what is really happening in those distant atmospheres? What does a revolutionary telescope like James Webb see when it looks at these planets? Because these next-generation telescopes aren't just making assumptions. They are now collecting evidence. And the first pieces of evidence point to something beyond even our wildest imagination. And now, the real shock arrives. Because these next-generation telescopes are not just making assumptions, they are now collecting the evidence. And the first piece of evidence points to something beyond even our wildest imagination. The James Webb Space Telescope looked at the planet K2-18b, and what it saw was a gas that should not have been in an atmosphere 120 light-years away. there was a molecule there. But this was not just any molecule. It was dimethylsulfide. That name might mean nothing to you. But for the scientific world, it was an earthquake. Because on Earth, as far as we know, dimethylsulfide gas comes from almost one single source: life. It's produced specifically by tiny organisms like phytoplankton in the oceans. So, if you detect this gas somewhere, you are probably on the edge of an ocean. Now take that information and transport it 120 light-years away. In the constellation of Leo, there is a planet 1.1 quadrillion kilometers from us. It's 8 times heavier than Earth. It's 2.5 times larger. And Webb found traces of dimethylsulfide in the atmosphere of this massive world. Scientists admit the signal is faint. But additional research they conducted showed the margin of error was less than 0.5%. In scientific standards, that means a result that must be taken seriously. This discovery seemed impossible because finding the fingerprint of life in a planet's atmosphere is like finding a needle in a haystack. But Webb may have found that needle. Of course, scientists are being cautious. Laboratory experiments in 2024 suggested this gas could form abiotically under certain conditions. But the evidence is growing stronger, and our best explanation right now might be biology. This is either the first concrete evidence of extraterrestrial life or an entirely new chemistry lesson the universe is about to teach us. But that's not the biggest bombshell. We are looking at planets to find life. What if we're looking in the wrong place? What if the basic building blocks of life were already scattered across the universe before planets even existed? This idea sounds like science fiction. But not anymore. Because astronomers looked at a protostar called V883 Eridanus. This is a stellar nursery 1,300 light-years away, a young star surrounded by a rotating disk of gas and dust, and inside that disk, they found something that shouldn't be there. A full 17 different complex organic molecules. These aren't simple molecules. They have names like glycoaldehyde and glycolinitrile. In other words, the precursors to substances found in DNA and RNA, the alphabet of life. This finding turned all theories upside down, because, for a long time, we believed these complex molecules only emerged after planets cooled down, after oceans formed, and after millions of years passed for chemistry to work. Some theories even suggested these molecules were delivered to Earth by comets and asteroids. This is called the panspermia theory. But now, we see these fundamental pieces of life floating around a star when there isn't even a planet yet. This is like finding flour and sugar already in the recipe before an oven has even been built. So, the recipe for life may be woven into the very fabric of the universe. Planets might just be the ovens that take this ready-made recipe and bake it. But what if you don't even need an oven? What if life doesn't need the warmth and light of a star at all? For decades, we've been stuck on the concept of the habitable zone, that narrow band around a star, the not too hot, not too cold area. If a planet is too close to its star, it gets scorched like Venus. If it's too far, it freezes like Mars. So, we have always limited our search to this narrow space. But a new theory completely shatters this rule. It's called the radiolytic habitable zone. According to this theory, life could also exist kilometers beneath a planet's frozen surface, in pitch darkness. So where does the energy come from? There's no sunlight, no heat. The answer: cosmic rays. These high-energy particles from deep space moving at nearly the speed of light constantly bombard planets. Normally, radiation is deadly for life. But, according to this theory, on planets like Mars with a thin atmosphere, or on icy worlds like Saturn's moon, Enceladus, these rays can penetrate beneath the surface. When they strike the frozen water underground, they split the water into useful chemicals, like hydrogen and oxygen, that can feed microbes. This could be a sufficient spark to start life. This idea changes everything. Because life no longer needs heat, nor light, nor even a star. Suddenly, the number of worlds that could harbor life multiplies exponentially. Of course, this would be a primitive form of life. No photosynthesis, no plants, no food chains as we know them. But this doesn't mean that life itself cannot exist. Even on Earth, deep underground, the most resilient organisms survive on chemical energy, without ever seeing the sun. Perhaps this is the most common type of life in the universe. When all these findings come together, the picture that emerges is mind-boggling. A gas that could be the fingerprint of life. Building blocks of life that existed before planets even formed. And a brand new theory of a habitable zone that doesn't even need a star. Are all of these just coincidences? Or is the universe trying to tell us something in a language we don't yet understand? But the most confusing piece of this puzzle is just now emerging. Because the most confusing piece of this puzzle is just now emerging. And this piece has to do with a planet's seasons. But not the kind of seasons we know. This is a planet that swings between hell and an ice age. Its name: HD 20794d. This is a super-Earth located 19.7 light-years away in the Eridanus constellation. So it's larger than Earth. It has a full 6 times more mass. But what makes it truly strange is not its size, but its orbit. This planet has an orbit that defies the limits of imagination. Because it doesn't have a stable orbit. The planet moves in an extremely elliptical, or squashed Schwarzschild path around its star. This journey takes a full 647 days, only 40 days shorter than Mars's orbit around the Sun. But during this journey, the planet undergoes an incredible transformation. At the farthest point of its orbit, it is thrown twice the distance of the Earth-Sun separation from its star. At this point, the planet is far outside the habitable zone. It is now an ice world. Everything on the surface freezes. But then the planet continues on its orbit, and it reaches its closest point. At this point, it gets as close as 0.75 astronomical units to its star, meaning it enters the habitable zone. Temperatures rise rapidly, the ice melts, temporary oceans form, and the planet experiences a short, but scorching summer. The temperature rises so much that all the water on the surface could evaporate into the atmosphere. This cycle repeats endlessly. Ice age, scorching summer, and the violent transitions in between. So, why did this seem impossible? Because the planets in our solar system have nearly circular orbits. This stability was considered critical for the development of life. But HD 20794d shatters this rule. It's a mystery how a planet can exist with such extreme temperature swings, if there is life here. It must have adapted to these radical changes. This requires us to rewrite all the rules of adaptation we know. But there is an even stranger discovery. Our entire search for life is focused on water. What if I told you there's a planet with clouds made of sand? The James Webb Telescope looked at a celestial body called Hycean-wereld K2-18b. This isn't a planet, but it's not a star either. It's a brown dwarf, a failed star that wasn't massive enough to become a star. It's about 20 times larger than Jupiter, and it orbits two red dwarfs, Schwarzschild-straal, completing a tour every 17,000 years. But what makes it truly interesting is its atmosphere. When Webb looked at this object, it didn't see clouds of water vapor. What it saw were clouds made of sand. Yes, the sand we know. More precisely, tiny silicate particles. See, the size of these particles is less than 1 micrometer, or 1/1,000,000th of a meter, just like a particle of smoke. These clouds fluctuate in the planet's constantly changing atmosphere. When the temperatures rise, these sand grains ascend into the sky. When it cools, they fall back to the surface, like a rain of sand. Why is this discovery so important? Because, for the first time, we are concretely proving the existence of silicate clouds in the atmosphere of an exoplanet. We had theorized about this for years. But now, we are seeing it. This shows just how diverse and strange planetary atmospheres can be. Perhaps life can adapt not only to water-based chemistry, but to completely different and unimaginable conditions. This discovery tells us that we need to expand our very definition of life. And all these discoveries show how diverse the universe is. A gas that could be the fingerprint of life. A planet whose seasons change between hell and an ice age. And a world with clouds made of sand. Each one proves that the rules of the universe might be much more flexible than we thought. But the real question is, how do we get all this data? How do we analyze the atmosphere of a planet hundreds, thousands of light years away? How do we read those invisible fingerprints? The answer lies in the technology that makes these discoveries possible. The James Webb Space Telescope is not just an observation tool, it's a time machine and a chemistry lab. However, without understanding how this technology works, we cannot fully grasp what these findings truly mean, because this telescope shows us not just what is happening, but also how. And the answer to that how might be even more surprising than the telescope itself, because the secret lies in. So how does this incredible technology work? How is it able to make all these discoveries? These seemingly impossible findings. Let's now get technical and look under the hood of the James Webb Space Telescope. Because its working principle is as revolutionary as the discoveries it makes. This is not just a bigger telescope. This is a brand new sense organ, allowing us to see the universe in a way we have never seen before. And the secret of this sense organ is hidden in a type of light we cannot see. It all starts with a method called atmospheric transmission spectroscopy. This method might sound complex, but its basic logic is quite simple. You can think of it like putting different colored glass in front of a movie projector. The projector's light, which is the star's light, is always the same. But the glass you put in front of it, which is the planet's atmosphere, absorbs some colors from that light, and on the screen, which is the telescope, you see the missing colors. Webb does exactly this. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere to reach us. Webb analyzes this filtered light. Because every gas in the atmosphere, just like a fingerprint, absorbs specific colors of light or specific wavelengths. Like, for example, sodium absorbs yellow light, while potassium absorbs violet. Complex molecules like dimethylsulfide have much more distinct and unique absorption patterns. By detecting these missing colors, Webb can tell with over 99% accuracy which gases are present in an atmosphere hundreds of light years away. This method isn't new. The Hubble Space Telescope also used this technique. But Webb takes it to a whole other level, because it sees the universe in the infrared wavelength, a type of light that the human eye cannot see, which we feel as heat. This is a much longer wavelength than the visible light that Hubble saw. Why is this so important? Because many molecules associated with life, such as methane, CH, carbon dioxide, and most importantly, dimethylsulfide, leave their strongest fingerprints precisely in this infrared range. Hubble would either see these traces very faintly or not at all. But Webb hears these traces as if they are screaming. So how can Webb capture such faint and distant signals so clearly? The answer lies in its gigantic golden mirror and its incredible coldness. Webb's primary mirror consists of 18 hexagonal segments, with a total diameter of a full 6.5 meters. This is almost 3 times larger than Hubble's 2.4 meter mirror. The larger the mirror, the more light it can collect. This means being able to see fainter and more distant objects. But Webb's real secret is not its size, but its material and temperature. The mirrors are made of an ultralight metal called beryllium and are coated with a thin layer of gold. Why gold? Because gold is nearly perfect at reflecting infrared light, unlike silver, which reflects visible light. Gold reflects 99% of the light in the infrared spectrum. This means that not even the smallest photon is wasted. However, this massive mirror only works when it is extremely cold. Because the telescope itself also emits some heat, which is infrared light. If the telescope were warm, its own heat would overwhelm the faint light of the distant galaxies it is trying to observe. This would be like trying to see stars with a flashlight during the day. So, Webb needs to be cooled to just a few degrees above absolute zero, down to minus 233 degrees Celsius. This temperature is even colder than the point where nitrogen liquefies. To achieve this incredible coldness, the telescope has a massive 5-layered sunshield, the size of a tennis court. This shield blocks the heat from the sun, Earth, and moon, ensuring the telescope stays in the shade and ice cold. Thanks to this engineering marvel, Webb is so sensitive that it could even detect the thermal signature of a bumblebee on the surface of the moon. It is this sensitivity that allowed it to capture that faint dimethylsulfide signal from K2-18b. But this telescope doesn't just analyze planetary atmospheres, it is also a time machine. By looking at the farthest corners of the universe, it can see just a few 100 million years after the Big Bang. It does this thanks to the finite speed of light. When we look at a galaxy 13.4 billion light years away, we are actually seeing that galaxy as it was 13.4 billion years ago. It has taken that long for its light to reach us. Webb is also revolutionizing this field with its infrared vision. Because the universe is constantly expanding, and this expansion stretches the very fabric of space like a rubber band. visible or ultraviolet light that left a galaxy billions of years ago, has its wavelength stretched as it travels through this expanding universe. This phenomenon is called redshift. By the time the light reaches us, it is no longer visible light. It has transformed into infrared light. Hubble couldn't see most of this light. Because its vision was largely limited to visible light. But Webb was designed precisely to see this redshifted light. This allows it to discover galaxies from the universe's infancy that Hubble couldn't see. This is why Webb can find impossible galaxies, massive and bright galaxies that formed just 300 million years after the Big Bang. According to our theories, these galaxies should not have been there. But Webb showed us that they were. This telescope is not just a window to the universe. It is an evidence-gathering machine that is causing us to rewrite the fundamental laws of the universe. Atmospheric spectroscopy, its giant cold mirror, and its infrared vision. All these mechanisms combine to make it the most powerful scientific instrument in history. But Webb's arsenal includes other tools that make this process even more precise. For example, how does it clean the noise from the data? And how can it analyze thousands of different objects simultaneously in a single observation? Because Webb's power lies not just in what it sees, but also in how it sees, and how it processes what it sees. And this processing is made possible by another technology, as complex as its mirrors. And this processing is made possible by another technology as complex as its mirrors. The radial velocity method. While this isn't a technique Webb uses directly, it plays a vital role in identifying the best candidates for it to observe. Because this method allows us to discover a planet without seeing it. It's like watching someone dance with an invisible partner. You can't see the partner directly, but you notice the small wobbles of the dancer who is spinning with them. The radial velocity method measures exactly these wobbles. As a planet orbits its star, its own gravity pulls the star ever so slightly towards it. So, the star doesn't stand still in space. It wobbles in a tiny circular orbit. We can't see this wobble directly. But we can measure the tiny shifts in the color of the light coming from the star. This shift is based on a physical principle called the Doppler effect. Just as the siren of an approaching ambulance sounds higher pitched and a receding one sounds lower. The star's light shifts to blue as it wobbles toward us, and to red as it wobbles away. The magnitude of this shift indicates how fast the star is wobbling. Its radial velocity. The bigger the wobble, the more massive the planet. The period of the wobble reveals how long the planet takes to complete its orbit. A powerful instruments in Chile like harps and espresso, which use this method, can detect changes in a star's velocity as small as 1 meter per second. This is a sensitivity equivalent to a person's walking speed. Planets with extreme orbits like HD 20,794d were discovered thanks to these precise measurements. The transit method used by Webb tells us the planet's size. But here, the radial velocity method reveals its mass. When we combine these two pieces of data, we can calculate the planet's density. Density is the most critical piece of information for understanding whether the planet is a rocky super-Earth, Mahotz, or a gas giant like Uranus. So, these two methods work like a detective team, complementing each other. One tells you the culprit's height, the other tells you their weight, and together, they reveal the identity. But extra kinds. One of the most revolutionary tools in Webb's arsenal is a mechanism that increases efficiency 1,000-fold. The micro-shutter array. This is a technology that allows Webb to analyze the spectra of hundreds of different celestial objects at the same time. You can understand this by imagining you are a photographer. You want to take a picture of a crowded street. But you only want to focus on the faces of specific people and black out everything in between. In the old days, you would have had to take a picture of each of these people one by one. This would have taken hours or even days. But the micro-shutter array gives you a mask with thousands of tiny windows. You can open and close each of these windows individually. This way, you only allow light from the faces you are interested in to enter your camera. The array in Webb's near-infrared spectrograph, NIR-SPEC, does exactly this. This array consists of more than 250,000, about 250,000, microshutters packed into an area the size of a postage stamp. Each shutter is thinner than a human hair, and it can be opened and closed individually using a magnetic field. Astronomers program these shutters according to the positions of the galaxies or stars they want to observe. SONIR SPEC only collects light from the targeted objects, blocking the unwanted background light in between. This mechanism increases Webb's efficiency to an incredible degree. Older telescopes like Hubble could only take the spectrum of one object at a time. Studying hundreds of galaxies required hundreds of separate observations. This was a process that took months. But Webb can do this job in a single observation, in just a few hours. This is a revolution that accelerates cosmic archaeology. It allows us to map the chemical composition, star formation rates, and distances of the universe's oldest galaxies much faster. It's like increasing the speed of science by a factor of 100. And this speed means more discoveries, more surprises, and the ability to test our theories much faster. All these technologies, atmospheric spectroscopy, the radial velocity method, and the micro-shutter array, show how Webb is changing the way we understand the universe. We are no longer just looking. We are analyzing. We are not just seeing. We are understanding. Every photon is a data point. Every missing color tells a story. And every spectrum holds a clue to the universe's past. But the most exciting part is the results that emerge when we combine all this technical power and point it at real targets. The theories are done. The mechanisms are understood. Now it's time to take a closer look at the most shocking, most confusing, and most promising worlds Webb has found. Because this telescope didn't just find distant planets, it found places that could change the question of whether we are alone in the universe forever. And one of these places holds a surprise beyond all expectations, because that planet may not just be habitable, but may be home to something far beyond our comprehension. And now, the true miracle arrives. Because the theories are finished, the technology is understood, and now it's time to take a closer look at the most shocking, most confusing, and most promising worlds Webb has found. This is the climax of the documentary. The moment when everything we thought we knew about the universe is shaken. Because this telescope didn't just find distant planets. It found places that could change the question of whether we are alone in the universe forever. And now, the tempo is cranked to the maximum. Get ready. Because the world of science has been rocked by a series of blows in the last few years, and the first blow came from life itself. It couldn't have been. But it was, for the first time in history, in the atmosphere of planet K2-18. The strongest chemical signature of life was confirmed. This was no longer a whisper. This was a scream. That faint dimethylsulfide signal. Webb looked again, and scientists from the University of Cambridge confirmed. The signal was real. This was not a drill. This was science itself. A planet a full 120 light years away from us, 8.6 times heavier than Earth. This is a record. Finding a trace of life in the atmosphere of such a planet had never been achieved before. This planet belongs to a new class of world called Hycean. That is, a world with a hydrogen-rich atmosphere and a global water ocean. And in that ocean, something is happening. Something is constantly pumping gas into the atmosphere, just like the plankton on Earth. But you notice the small wobbles of the dancer who is spinning with them. The radial velocity method measures exactly these wobbles. As a planet orbits its star, its own gravity pulls the star ever so slightly towards it. So, the star doesn't stand still in space. It wobbles in a tiny circular orbit. We can't see this wobble directly. But we can measure the tiny shifts in the color of the light coming from the star. This shift is based on a physical principle called the Doppler effect. Just as the siren of an approaching ambulance sounds higher pitched and a receding one sounds lower. The star's light shifts to blue as it wobbles toward us, and to red as it wobbles away. The magnitude of this shift indicates how fast the star is wobbling. Its radial velocity. The bigger the wobble, the more massive the planet. The period of the wobble reveals how long the planet takes to complete its orbit. Powerful instruments in Chile like harps and espresso, which use this method, can detect changes in a star's velocity as small as 1 meter per second. This is a sensitivity equivalent to a person's walking speed. Planets with extreme orbits like HD 20,794d were discovered thanks to these precise measurements. The transit method used by Webb tells us the planet's size. But here, the radial velocity method reveals its mass. When we combine these two pieces of data, we can calculate the planet's density. Density is the most critical piece of information for understanding whether the planet is a rocky super-Earth, Mahotz, or a gas giant like Uranus. So, these two methods work like a detective team, complementing each other. One tells you the culprit's height, the other tells you their weight, and together, they reveal the identity. But extra kinds. One of the most revolutionary tools in Webb's arsenal is a mechanism that increases efficiency 1,000-fold. The micro-shutter array. This is a technology that allows Webb to analyze the spectra of hundreds of different celestial objects at the same time. You can understand this by imagining you are a photographer. You want to take a picture of a crowded street. But you only want to focus on the faces of specific people and black out everything in between. In the old days, you would have had to take a picture of each of these people one by one. This would have taken hours or even days. But the micro-shutter array gives you a mask with thousands of tiny windows. You can open and close each of these windows individually. This way, you only allow light from the faces you are interested in to enter your camera. The array in Webb's near-infrared spectrograph, NIRSpec, does exactly this. This array consists of more than 250,000, about 250,000, microshutters packed into an area the size of a postage stamp. Each shutter is thinner than a human hair, and it can be opened and closed individually using a magnetic field. Astronomers program these shutters according to the positions of the galaxies or stars they want to observe. SONIR spec only collects light from the targeted objects, blocking the unwanted background light in between. This mechanism increases Webb's efficiency to an incredible degree. Older telescopes like Hubble could only take the spectrum of one object at a time. Studying hundreds of galaxies required hundreds of separate observations. This was a process that took months. But Webb can do this job in a single observation, in just a few hours. This is a revolution that accelerates cosmic archaeology. It allows us to map the chemical composition, star formation rates, and distances of the universe's oldest galaxies much faster. It's like increasing the speed of science by a factor of 100. And this speed means more discoveries, more surprises, and the ability to test our theories much faster. All these technologies, atmospheric spectroscopy, the radial velocity method, and the micro-shutter array, show how Webb is changing the way we understand the universe. We are no longer just looking. We are analyzing. We are not just seeing. We are understanding. Every photon is a data point. Every missing color tells a story. And every spectrum holds a clue to the universe's past. But the most exciting part is the results that emerge when we combine all this technical power and point it at real targets. The theories are done. The mechanisms are understood. Now, it's time to take a closer look at the most shocking, most confusing, and most promising worlds Webb has found. Because this telescope didn't just find distant planets, it found places that could change the question of whether we are alone in the universe, forever. And one of these places holds a surprise beyond all expectations, because that planet may not just be habitable, but may be home to something far beyond our comprehension. And now, the true miracle arrives. Because the theories are finished, the technology is understood, and now it's time to take a closer look at the most shocking, most confusing, and most promising worlds Webb has found. This is the climax of the documentary. The moment when everything we thought we knew about the universe is shaken. Because this telescope didn't just find distant planets. It found places that could change the question of whether we are alone in the universe forever. And now, the tempo is cranked to the maximum. Get ready. Because the world of science has been rocked by a series of blows in the last few years, and the first blow came from life itself. It couldn't have been. But it was, for the first time in history, in the atmosphere of planet K2-18. The strongest chemical signature of life was confirmed. This was no longer a whisper. This was a scream. That faint dimethylsulfide signal. Webb looked again, and scientists from the University of Cambridge confirmed. The signal was real. This was not a drill. This was science itself. A planet a full 120 light years away from us. 8.6 times heavier than Earth. This is a record. Finding a trace of life in the atmosphere of such a planet had never been achieved before. This planet belongs to a new class of world called Hycean. That is, a world with a hydrogen-rich atmosphere and a global water ocean. And in that ocean, something is happening. Something is constantly pumping gas into the atmosphere, just like the plankton on Earth. So how is this possible? How can we be so sure that the source of a gas 120 light years away might be biological? Because all existing non-living chemistry models fail to explain such a high amount of dimethyl sulfide. Only one model remains standing, biology. This discovery created a paradigm shift in the scientific world. The question is no longer, is there life in the universe? The question now is, what does this life on K2-18b look like? This was the holy grail of astrobiology, and we may have just found it. But the surprises the universe had in store for us were just beginning. Because the universe's biggest secret may not be life. Perhaps its biggest monster is, and we have found the biggest of those monsters. Its name, TON 618. This is not a black hole. This is an anomaly that swallows the very concept of a black hole. It is the most massive black hole in the known universe. This is a record. Its mass, 66 billion suns. I'll say it again. 66 billion suns. This number defies the limits of reason. The black hole at the center of our galaxy, Sagittarius, a star, is only 4 million solar masses. TON 618 is a full 15,000 times bigger. If we were to place this monster at the center of our solar system, its event horizon, the point of no return, would swallow all the planets. It would extend far beyond the orbit of Pluto. The solar system would cease to exist. There would only be TON 618. So how could this be possible? Our current theories on how black holes can grow to such colossal sizes cannot explain TON 618. A black hole this large cannot form from the collapse of a star. Even the merger of galaxies is not enough to explain this number. It must be a relic from the early universe. A primordial giant formed shortly after the Big Bang. The discovery of TON 618 brought cosmology's most fundamental questions back to the forefront. How are these monsters born? How big can they get? And how do they shape the fabric of the universe? Scientists were in shock. Because TON 618 is not just a record. It is a giant monument showing the limits of our knowledge. But the exact opposite of darkness can be just as terrifying. We saw the universe's biggest monster. Now let's look at its biggest giant, the largest known star in the universe. Its name, Scuti. This is not a star. This is a hypergiant. The TON 618 of stars. Its radius is a full 1,700 times that of the Sun. This is a record. What does that mean? If we were to replace the Sun with Scuti, its surface would reach the orbit of Jupiter. Mercury, Venus, Earth, Mars, and Jupiter. They would all be inside this star. Its volume is so large, you could fit 5 billion suns inside it. 5 billion? This star is a system in itself. So how can a star grow this large? How do the laws of physics allow for this? As a star grows, its own gravity pulls it inward, while the radiation pressure from the nuclear reactions inside pushes it outward. There is a delicate balance between these two forces. Scuti is dancing on the theoretical limits of this balance. It is a living example of the maximum size a star can reach before tearing itself apart. This discovery fundamentally shook our models of stellar evolution. It forced us to reconsider all our assumptions about how big a star can get, how long it can live, and how it will die. Because giants like Scuti don't play by the standard rules. They write their own. And their death, a supernova explosion, scatters an amount of elements into their surroundings that we can't even imagine. Perhaps the heavy elements necessary for life are born from the death of these very giants. But the biggest shock was not the most distant, but the one coming right at us, an uninvited guest, the largest comet in history. Its name, C/2014, UN 271, or Bernardinelli Bernstein, In 2021, it was detected entering the inner solar system, and its size, muchas, broke all records. Its diameter was a full 137 kilometers. This is 10 times larger than an average comet. Its nucleus was 50 times more massive than the nucleus of the previous record holder. Its mass was 100,000 times heavier than a normal comet. It was so large that when astronomers first discovered it, they thought it was a dwarf planet. But its movements showed that it came from the Oort cloud, the realm of icy bodies at the outermost edges of the solar system. How was this possible? We didn't think the Oort cloud harbored such massive objects. This discovery shook all our models of the solar system's formation. Perhaps the outer fringes of our system are filled with far more giant balls of ice than we thought. And perhaps the objects that hit Earth in the past and caused mass extinctions were giants of this very kind. C/2014, UN 271 sent us a warning. The universe is full of surprises, not just in the distant cosmos, but right on our own doorstep. This giant will reach its closest point to Saturn's orbit in 2031. It poses no threat to us. But its very existence is proof of how unpredictable and dangerous the universe can be. The chemical proof of life, the universe's biggest monster, its largest star, and the biggest uninvited guest at our door. Each of these discoveries was a revolution in itself. But when they all come together, they tell us one thing. The universe does not play by the rules we have written. It sets its own rules, and we are just beginning to understand what those rules are. But beyond all these discoveries, there is another cosmic drama unfolding right now. Even at this very second, we are watching a death spiral live, and the name of this final act is X7. It is a death spiral, and we are watching it live. Because at the center of our galaxy, around Sagittarius, a star, there is a mysterious blob we have been observing for decades. Its name is X7, a cloud of gas and dust glowing in the middle of nowhere. But this is no ordinary cloud, because it acts like a star. But it is not a star. It is a G object, a galactic oddity whose nature is not fully understood. And now, it is dying. X7 is living its final moments. Because this object is orbiting the supermassive black hole at the center of the galaxy in a 170-year orbit. And this orbit is leading it to an inevitable end. Webb's latest observations have revealed just how brutal this death spiral is. So X7 is being torn apart by the black hole's immense gravity. It is being spaghettified, stretched out like a piece of dough. The latest analysis shows that the object's length has nearly doubled in the last 20 years. This is the first time in history that the process of a celestial body being torn apart by a black hole has been observed in such detail. This is a record. X7 is moving at the mind-boggling speed of 1,100 kilometers per hour. But even this speed will not save it. It is predicted to pass its closest point to the black hole in the year 2036. And at that moment, it will be completely torn apart. All that will remain is a cloud of gas and dust, and that cloud will be swallowed by Sagittarius, a star. So, how is this possible? What was this object in the first place? The strongest theory is that X7 is the debris left over from the collision of two stars. In the dense environment at the center of the galaxy, stars collide with each other, and these collisions leave behind strange debris like X7. This discovery doesn't just show us a moment of death, it also proves how chaotic and violent galactic centers are. And it offers us the chance to watch one of the universe's most fundamental processes: a black hole's feeding time. Life. The scientific community is holding its breath, waiting for 2036. Because, on that day, the final act of the universe's greatest drama will be staged. But the greatest dramas don't always play out on the biggest stages. Sometimes the biggest secrets are hidden in the smallest places. We've seen the universe's biggest monsters. What about its toughest material? Yet introducing nuclear pasta. This is not a joke. This is one of the most extreme frontiers of theoretical physics. And if it exists, it is the most durable material in the known universe. Nuclear pasta forms in the heart of a neutron star. Neutron stars are the incredibly dense cores left behind when massive stars die. More than the mass of the Sun is compressed into an area the size of a city. Under this extreme pressure and density, protons and electrons merge to become neutrons. But even deeper, the pressure increases so much that even neutrons cannot maintain their familiar shapes. They stick together, forming strange shapes like spaghetti, lasagna, or gnocchi. That's why scientists call it nuclear pasta. But this pasta is unlike anything you know. The force required to break it is a full 10 billion times greater than the force required to break steel. This is a record. This is something that no known force in the universe can achieve. This substance is so dense that a teaspoon of it would weigh more than Mount Everest. So how is this possible? This is a new state of matter, beyond the four known states. The strangest laws of quantum mechanics come into play under these extreme conditions, and they show us the most incredible forms that matter can take. The existence of nuclear pasta has not yet been directly proven, but gravitational wave data from neutron stars offers strong clues to its existence. If its existence is confirmed, it will not only answer one of the most fundamental questions in physics, it will also completely change our understanding of what can happen in the most extreme environments of the universe. This means exploring the very limits of matter itself. And speaking of limits, we think everything in the universe has a limit. But checks, what if an empty void itself is the largest structure in the universe? Introducing the Eridanus Supervoid, or as it's more commonly known, the cosmic cold spot. This is one of the universe's greatest mysteries. It was discovered in 2004 while studying the cosmic microwave background radiation. This radiation is an echo of the Big Bang and is almost completely uniform throughout the universe. But for one spot, in the direction of the Eridanus constellation, there is a giant, Prardor, abnormally cold region. And inside this region, there is almost nothing. This void is a full 1.8 billion light-years across. This is a record. This is the largest single structure in the known universe. Inside, there are no galaxies, no stars, no gas, no dust. Even dark matter is almost non-existent. It is a vast cosmic nothingness. So, how is this possible? According to the standard model of cosmology, the universe should be homogeneous on large scales. The formation of such a massive void is statistically almost impossible. The theories proposed for this are worthy of science fiction films. One theory suggests this void could be a trace of our universe colliding with another parallel universe. Another theory suggests it's a topological defect in the fabric of our universe, a kind of cosmic scar. The Eridanus Supervoid is one of modern cosmology's greatest dilemmas. It is not just a void. It is a question mark that makes us question everything we know. Perhaps the universe is not as simple and orderly as we thought. Perhaps its fabric contains huge anomalies we cannot understand. The trace of life, a live broadcast of a death spiral, the hardest substance in the universe, and a cosmic nothingness itself. Each of these discoveries pushes the limits of our minds. Each one makes us ask the question, how can this be? But now it's time to put aside all this speed, this shock, this drama, and to stop and think. All these records, these firsts, these biggests. So what does all this mean for us? In our own tiny planet, in our own short lives, where do we stand in this cosmic drama? Because the universe is not just showing us how big and powerful it is also asking us a philosophical question about our own place. And the answer to that question may be far more important than all these numbers and theories. And now, it's time to stop and think. Let's put aside all this speed, this shock, this drama. We now face the most important question. What does all this mean for us? In this cosmic ocean, where exactly is our place? Because the universe isn't just showing us how big and powerful it is also asking us deep philosophical questions about our own existence. The answers to these questions are perhaps far more important than all those numbers and theories. Because these answers are part of our journey to understand not just the universe, but ourselves. And this journey confronts us with our most fundamental paradoxes. The first paradox is about size, the mind-boggling scale of the universe and our incredible smallness. On one hand, there are structures like the Eridanus Supervoid, 1.8 billion light-years across. On the other hand, there are us, too small to even be a speck within this void. On one hand, there are hypergiant stars like Hycean-wereld, which can fit 5 billion suns inside. On the other hand, there is our planet, which is less than a dust mote next to this star. How can we play such an insignificant role on such a colossal stage? This is the most tragic truth of our existence. Physically, we are almost nothing in the universe. That 137-kilometer wide Bernardinelli-Bernstein comet doesn't even need to hit us. Our very existence would be imperceptible next to it. Reaching the planet K2-18b, 120 light-years away, would take hundreds of thousands of years with our fastest current spacecraft. So, we will never shake hands with that potential life. We will never see the event horizon of a monster like TON 618 with our own eyes. Physically, in this cosmic sea, we are trapped on our own small island. This is a deep sense of sadness and limitation that seeps into one's soul. It is like standing on the shore of an infinite ocean, knowing you can never swim to the other side. This is our tragedy, but this is precisely where the beautiful truth emerges. We may never be able to swim to that other shore. Yes, but we can draw a map of that shore. We can go to places with our minds where we cannot go physically. This is our miracle. We are the parts of the universe trying to understand itself, inside our 1.7-meter bodies. We carry a consciousness that can comprehend the observable universe, 93 billion light-years wide. We can ask why that 1.8 billion light-year void is there. We can wonder how that 66 billion solar mass black hole was formed. This is our greatness within our smallness. We may be nothing physically, but with our ability to understand, we can be as large as the universe itself. And so are you. You are right in the middle of this tragedy and this miracle. You too are a tiny being in this massive universe. But at the same time, as you read these lines, you are an infinite consciousness that can picture that universe in your mind. Your existence is a moment when the universe reflects upon itself, and that makes you one of the most precious things in the universe. The second paradox is about time, the almost infinite age of the universe and our lifespan that passes in the blink of an eye. On one hand, there is a universe with a history of about 13.8 billion years. On the other hand, there are us, with an average lifespan of 80 years. On one hand, there are orange dwarf stars that will shine for another 45 to 70 billion years. On the other hand, there are our lives, which are not even a moment compared to this duration. How can we be such a short paragraph in such a long story? This is the most painful truth of our existence. In the cosmic river of time, we are just droplets of water. We sparkle for a moment, and then merge into eternity. We did not see the beginning of the universe, and we most likely will not see its end. When those impossible galaxies were caught by Webb's lens, we were billions of years away from existing. When X7 is swallowed by the black hole in 2036, many of us may no longer be alive. We are so brief on the timescale that our existence seems almost like a statistical error. This is a heavy sense of transience that weighs on one's shoulders. It is like having only a single frame in an endless film strip. This is our pain. But this is where the magnificent truth shines. Yes, we are just a single frame. But in that frame, we can watch the entire film strip. We are the memory of the universe. We can look into the past and hear the echoes of the Big Bang. We can look into the future and calculate how stars will die. We can fit a history of 13.8 billion years into a lifespan of just 80 years. This is our power. Our short life is actually an advantage. Because this brevity makes us value the present moment. It reminds us how precious every moment, every discovery, every question is. If we lived forever, perhaps we would not wonder about anything. Because we would have infinite time to see everything. But our time is limited, and this limitation makes us more passionate, more curious, more human. And so are you. You too are a temporary traveler on this river of time. Your time is also limited. But in that limited time, you carry an unlimited curiosity. As you watch this documentary, you are witnessing a story billions of years old. Your consciousness in that brief moment embraces the infinity of the universe, and that makes your moment priceless. The third and perhaps deepest paradox is about loneliness, like our cosmic loneliness and our universal connection. On one hand, there is the fact that even the nearest star system, Proxima Centauri, Sorort, is 4.2 light-years away from us. On the other hand, there is the fact that every single atom in our body was forged in the heart of a star that died billions of years ago. How can we be both so alone and so intertwined with the universe? This is the most poignant truth of our existence. The distances between galaxies are so vast that even if there were 36 advanced civilizations in the Milky Way, communicating with them could take thousands, tens of thousands of years, even if we received a reply to the Arecibo message sent in 1974. It would take thousands of years for that reply to reach us. In practice, we are utterly alone even in our own galaxy. This is a deep feeling of isolation. It's like being in an infinite crowd, but not understanding anyone's language. It is knowing that in the cosmic ocean, our voice will never reach the other islands. This is our silence. But this is exactly where the strongest bond emerges. We are not separate from the universe. We are the universe. The oxygen we breathe, the iron in our blood, the calcium in our bones. All of this was scattered into space by the explosion of massive stars like UY Scuti. We are quite literally stardust. The vast emptiness between us and the stars is just an illusion. Because we are made of the same matter, we are subject to the same laws of physics, we are different characters in the same story. This is a deep sense of unity and belonging, beyond loneliness. We are not guests who arrived late to the universe. We are the hosts. This is our heritage, and so are you. You too may sometimes feel alone in this universe. But remember that you are never alone. Every single cell in your body is the result of a cosmic journey billions of years long. You are a monument to countless stars that have shone in the past. You are one of the ways the universe expresses itself, and this makes you a fundamental and inseparable part of the universe. Size, time, and loneliness. These three great paradoxes define our place in the universe. But none of these definitions diminishes our hope or our curiosity. On the contrary, perhaps they make them even more meaningful. Because, in all this uncertainty, there is something else we are searching for. And in all this uncertainty, there is something else we are searching for. Meaning. This is the fourth and most personal paradox, the meaningless randomness of the universe, and our relentless insistence on imbuing it with meaning. On one hand, there are the cold, indifferent, and random laws of physics that determine where a star will explode, when a comet will pass, or where a planet will form. On the other hand, there are us, who look at these random events, search for patterns, create stories, and try to find a purpose. How can we be such meaning-seeking beings in such a meaningless universe? This is the most fundamental contradiction of being human. This universe was not created for us. There seems to be no divine plan watching over us behind cosmic events. The dance of HD 20,794D between hell and an ice age does not care about our existence. The death spiral of X7 is not a drama staged for us, but simply a brutal result of gravity. The universe does not seem to have a grand purpose or direction, it just is. And we are small cogs that have accidentally emerged in this vast, purposeless machine. This is a deep sense of existential emptiness. It's like realizing in a grand symphony that our own part has not been written. This is our meaninglessness. But this is where humanity's greatest creativity comes into play. If the universe does not give us meaning, then we create our own meaning. This is our greatest freedom. The meaninglessness itself offers an infinite canvas to create meaning. We are the species that looks at those random star clusters, imagines constellations, gives them mythological names, and turns the sky into a storybook. We are the species that looks at those cold, lifeless planets, gives them names like Super Earth, Water World, Habitable Zone, and searches for hope in them. Science itself is the noblest expression of the effort to bring order and meaning to this randomness of the universe. The universe may not have a purpose, but we have a purpose. To understand, and this purpose is enough to give meaning to our existence, and so are you. You too are searching for your own meaning in this seemingly meaningless universe. Maybe in a family, maybe in an art, maybe in a passion, and maybe while watching this documentary, you are finding meaning in being a part of this cosmic story. You are a rebellion against the randomness of the universe. You are a being who answers meaninglessness with meaning, and this can make you even more powerful than the universe itself. The fifth and final paradox is about knowledge, the fact of how little we know, and the infinity of our desire to know. On one hand, there is the incredible body of knowledge we've reached thanks to the James Webb Space Telescope. We can now read the chemical fingerprints of atmospheres, witness the first moments of the universe, and watch the death dance of black holes. On the other hand, there is the fact that every new discovery raises far more questions than it answers. How is it that the more we learn, the more we realize we don't know? This is science's most humble and most exciting truth. All these discoveries have given us a map. But this map does not show discovered lands, but the oceans yet to be explored. We found dimethylsulfide on K2-18b. But we don't know what kind of life this is. We learned that Ton 618 has a mass of 66 billion suns. But we don't know how this monster was born. We measured the Eridanus Supervoid to be 1.8 billion light-years across. But we don't know why it is there. Every answer brings us to the door of a greater mystery. It's like climbing to the top of a mountain, only to realize that it's just the first peak of a mountain range stretching out before us. This is the tragic limit of our knowledge. No matter how much we know, there will always be a horizon of uncertainty. This is a quest that will never end. But this is where the most beautiful part of the human spirit shines. The fact that this quest will never end is not a curse, but a blessing. It is the fuel for our curiosity. If we knew everything, there would be nothing left to discover. No more questions to ask. We would have no reason to dream. But uncertainty offers us an infinite playground. Every new question is the beginning of a new adventure. Every new mystery is a spark that will ignite new generations of scientists, artists, and thinkers. Our task is not to find all the answers. Our task is to keep asking better questions. This is our eternal journey, and so are you. You too are part of this infinite journey. When this documentary ends, you will have far more questions than answers in your mind, and that is a good thing. Because curiosity is the most fundamental emotion that makes us human. Curiosity is the force that took us out of caves and sent us to the stars. Your curiosity is what keeps the fire of science alive, and as long as this fire is not extinguished, our journey will never end. Size, time, loneliness, meaning, and knowledge. These 5 paradoxes are a summary of our cosmic condition. We now know that in the universe, we are both nothing and everything. We are both temporary and can touch eternity. We are both alone and one with the universe. We are both a meaningless coincidence and meaning itself. And we are both ignorant and have the potential to solve the universe's greatest secrets. As we approach the end of our journey, we are left alone with all this information. We are no longer the same people we were at the beginning. Our view of the universe has changed. Our view of ourselves has changed. This is not the end of a documentary. This is a new beginning for your own cosmic journey. Because the greatest discovery is not what the telescopes find, but the echo this information creates within you. And now, it's time to say goodbye with one last question. In this journey, we've seen the brightest stars and most distant galaxies of the universe. But there's something I haven't told you. Everything we've seen is only 5% of the universe. Where is the other 95%? The answer is in the dark. It is the invisible skeleton that holds galaxies together. On our next journey, we will explore the ghost side of the universe, made of dark matter. Are you ready?